Okay. If I had my choice, you would all have completed Math 20 before we did this course, because there's a lot of little things that can help. For one, the quadratic formula. If you know how to use the quadratic formula already, it's very useful when you're trying to solve the d equals vit plus 1 half at squared, trying to solve that formula for t. So the more experience you have with it, obviously, the better you'll do. This is one of the lessons where it really helps if you've done all of your trigonometry. Unfortunately, I had to make a choice for you guys in grade 11 here. I had to either do algebra first, or I had to do trigonometry first. So the very last example I'm going to do today, there is a shortcut way of doing it, which you guys who've done math before will know because we've done the cosine law. And the cosine law will save you so much time. You guys in grade 11, I'll show you the cosine law. We haven't actually covered it thoroughly in math class. You're welcome to try it, but it totally would help if you've done math 20 all the way through. But that's just kind of, that's what it is, right? Okay, let's get started. The term we're going to do today is called vectors, and we've used that word before. Vectors basically means there's a direction and an amount to it. See it sitting under the cosine law? It's on the formula sheet, yeah. We did it last year. It's the one that has cosine in its formula. There's only one on there that has cosine, right? Oh.
Yeah, I think it's the last.
Whatever, we'll do it today. Okay, sometimes what we'll do when we have problems is we'll draw arrows to represent vectors. It's a pretty straightforward way of trying to keep track of what's happening. For example, I'm going to fast forward really fast through my notes here just to find a slide that would make sense. Let's say that I wanted you to try to figure out how far it was across a soccer field. Rather than actually drawing in a soccer field, maybe the best thing to do would be to say, well, you'd have to walk all the way along one length right here. I'd use an arrow, right? And then you could walk all the way around this length right here. I'd use an arrow. Okay. Well, if I actually cared about my start to my finish, right? My start would have been right here. My finish would have been right here. I'll just use an arrow to try to indicate where I've actually traveled. A vector being a magnitude, so however far this happens to be, and a direction. So maybe some of you can see where this is going to go. We're going to start bringing in some trigonometry, where we need to use angles, things like Pythagoras' theorem, and if you know how, again, the cosine law. So let me go back to the stuff that I skipped over here. Technically, we can do vectors in 3 dimensions. You can go in the up and down direction, the y direction, the side-to-side direction, the x direction, and you technically can like come out of the page, if that makes sense, in the z direction. But we don't cover the z direction. We're only going to do things in 2 dimensions in this course. But it is possible to do the third. No. I mean, I covered some of that in like one of my university level physics courses, but usually we just do the 2 dimensions.
What even would go that way?
Well, so like imagine that I'm like here, straight. This would be just the x dimension, right? If I were to throw it like this and start getting some y dimension in, and if I were to tip it and go this way, see how I'm doing x, y, and z? X, y, z. Usually what we do though, if I'm throwing it in this direction then, what I do is I recalibrate my axis so that rather than that right here being the axis right there, if I'm throwing it this way, I just recalibrate the axis so that that's now the direction it was always going on. You know what I'm saying, right? So usually there's a quick fix for that. Okay. Long story short about the arrow thing, really, I mean, if you have a distance or a velocity that's this far and you add this much more to it, I mean, really the length of your arrow is meant to be an indicator of how strong something is. So if you have a little arrow, that means that it's only going this far, and if you have a big arrow, it means it's going further, right? That's just kind of intuitive. What if something is going backwards? Well, then you just subtract. So, truth be told, this is going to be really, really intuitive. Like, this will make sense. Okay, let's talk about some vector conventions. First one, draw the arrow in the direction it's traveling. Makes sense, right? Whichever way you're going, that's the direction the arrow goes. If you need to write a direction not using like an arrow, use like square brackets. Like it's going north, something like that. When you're drawing to the best of your ability, make sure the length of the vector is proportional to the magnitude. Let me give you an example of something that would not work. I'm going to tell you that this vector right here is 3 meters. and I'm going to tell you that this vector right here is 2 meters. Well, that's going to, right off the bat, that's going to cause you problems, isn't it? Right? I don't need you to take a ruler and make it like absolutely perfect, but I mean, if you were then going to try to figure out how far it is from start to finish and try to find this distance right here, I might look at that and say, I don't know, maybe that's supposed to be, well, if that's a 2, then this maybe is a 2.1, but like that might not even make sense, right? Because my arrows are all out of whack. So try to make sure it's proportional. So don't do that. You're actually allowed to pick up a vector and move it around, so long as it just maintains the same magnitude and direction. That one will make more sense once I show you it in an example. And this last one will probably also make more sense once I start doing an example. The idea is we always want to have them go tip to tail. Again, I'll just read it for now and then we'll do an example. So, here's what I just talked about with Andy a few minutes ago here. We're just going to work with 2 dimensions. We're only going to do the x and y components. So let's start with a basic example here. This is the one I started with. Let's say I asked you how far it was across the soccer field. This is where you're starting. This is where you're finishing. And let's say you got to know a couple of values. You knew that the length of the field along one side here was 120 meters. And then the width right here is 90 meters. Could you calculate how far it is across the field? Actually, I think it tells you. It says it's 150 meters. If it didn't tell you it was 150 meters, though, do you guys know how you'd calculate it? What's the formula? Yeah, Pythagoras' theorem, right? A squared plus b squared equals c squared. I don't think it really matters what you choose to be a and b, right? So let's let this side over here be a. So 120 meters squared plus this side here will be 90 meters squared equals c squared. Just need a calculator. $120 squared plus 90 squared. Well, hopefully if we do it right and we square root it, hopefully this picture's right. Is it 150? Yeah. Okay, good. Right. So if I square root it, I do indeed get the 150. You guys are all fairly familiar with how to use Pythagoras' theorem. So that's good. You should have picked it beforehand. We're not done though. This is why we need vectors. Okay, you might be wondering what's the whole point of this, Chris. The point though is that a vector has a magnitude and a direction. We have the magnitude. We know that it's going to be 150 meters. But what I need to do is know a direction value as well. I need to put something in a bracket afterwards. And when it comes to physics, what I could do is I could suggest that it looks like it's going more or less northeast. But that's probably not sufficient. I need to know exactly what angle it's traveling at northeast. What we need to do is we need to try to find this angle right here in the corner as well. Have you ever had to solve for an angle in a corner like this? Adjacent over. That'll work. That'll work. Let me just do a quick review. You guys ever heard of SOHCAHTOA? SOHCAHTOA? I would recommend that 9 times out of 10, the TOA part is actually the most efficient, because that's probably what the information you're going to have is. Based on this little angle right here, this side over here would be your opposite side of a triangle. This side over here would be the adjacent side of a triangle. And this side over here would be the hypotenuse side of a triangle. Now, granted, we know all 3 numbers. We know the adjacent, we know the opposite, we know the hypotenuse. The advice I'd give, though, the 150 was a number we just calculated. It's usually better form if you can avoid using a number that you calculated in the course of the question. Because what if you made a mistake? Or what if you rounded? Does that make sense? So although you could do opposite over hypotenuse, adjacent over hypotenuse, my recommendation would be to write out that tan of our angle would be the opposite over the adjacent, because both of those are values that we were given in the question rather than we solved for. So this triangle, the opposite value would have been 90 meters. The adjacent value would have been 120 meters. How in the world do you get an angle out of that? Again, it really helps if you've done the grade 11 math component, because we did a lot of this last year. You guys over here. How do you get it by itself? Say that louder. What did you do?
You have to do like the second and then the 10.
That works there. I'm going to change the vocabulary for you. Andy, you're right. You got to do like this tan button right here. The word we're going to use for this, though, it's called an inverse tan. That's what it's referred to as. Think of it this way. It's the opposite. You know how adding the opposite is subtracting, multiplying the opposite is dividing? This thing right here, tan to the minus 1, essentially what it would do is it would cancel out the tan on both sides here. But I can't just do a tan minus 1 on one side. I'd have to tan minus 1 on the other side as well. So you have to, what's called, the verb we would use, or the vocabulary would be inverse tan 90 over 120.
Michelle, could you check my settings?
Yeah, that's the next thing I'm going to point out here. If you're not getting 37 or so degrees right here, it may be because your calculator is set to radians. And that's what I'm thinking yours is going to be. So to find that, click on mode, which is right next to the second button here.
Yeah.
You want to be on degrees, not radians. So just a quick reminder for you guys, radians, we talked about this last year. Radian is like that perfect slice of pizza. You know what I'm talking about this at all? Right? Which is another way of measuring angles. Right? And so a radian would be if this angle right here, if this is 2 and that is 2 and that is 2, that's considered a radian. We don't want to work with that in physics, so you can go ahead and check. You guys over here in grade 11, if I lose you on some of this trig stuff, please let's talk later, okay? Because you're at a little bit of a disadvantage. Sorry, I don't have a great way to solve that though. Let me know if I do lose you. I wouldn't expect you to have known this radians thing though. That'd be brand new to you. And same thing for you guys through the computer there. If you're lost on some of the math section here, email me. Let's see if I can help try to troubleshoot that. Okay. SIGDIG rules still do apply the same way. How many SIGDIGs should I get on this degrees value? Yeah, 2, right? So let's make it 37 degrees. Here's how we might write this then. I'm going to change up the way this would work. So I would say it's 150 meters, but this angle right here is 37 degrees we just calculated. We'd actually write it probably like this. We would say you need to go mostly east, because east is like this direction here. Then you've got to start swinging 37 degrees up in the northern direction. And that's the way we would write that. So this would now be our vector. 150 meters is our magnitude. Start traveling east, but actually swing 37 degrees up towards the north. That makes sense for our kind of first example. Okay, let's spend a couple slides talking about the different ways you can actually record degrees. One of them is known as the polar coordinates method. And again, it helps if you've done math. Unfortunately, not all of you have done this. In math, we often define this axis right here as being 0 degrees. And as you go around the circle like this, you add more to it. This is one option. So if you're going directly east, east is actually known as 0 degrees. North would be known as 90 degrees. West would be known as 180 degrees. And south would be known as 270 degrees. That's one option. So that's a very mathematical kind of thing. If you know the term standard position in math, that's an option. 9 times out of 10, I'm going to prefer this method here. It's called the navigator method, and it's what I just showed you. You could write it a little bit differently than I just did, but it's kind of the same concept here. You base it on north, south, east, and west, and you measure the angle in relationship. So like, here's another way of writing it: 60 degrees south of west. See how this angle right here would be 60 degrees. Here you kind of change the order here. You've got to go, like, west is the normal direction you were traveling, and you've got to go south of your west by 60 degrees. The other way I might write this would be to say you're mostly going west, but then you've got to go 60 degrees towards the south. See how they changed the order here though? Here it's south of west, and then here I'm writing it as go west, and then go 60 degrees to the south. They all kind of mean the same thing. I don't really care which one you pick, but I just need you to be familiar with how to write an angle. That's all. That's our goal today, essentially. I've kind of given you like the overview here. We're now going to work with things in 2 dimensions. Rather than it just being on a straight line track of like Hot Wheels going down there, now we have to deal with angles. Angles is going to involve trigonometry. The best way of doing trigonometry is by using, I'm going to use my air quotes here, vectors, where we draw arrows, we make triangles, and those triangles are things that we can solve. So, let's do some examples. Sometimes the best way to learn is just to example you to death. So, you're in a car. You're driving 10 kilometers east, then you apparently come to a 4-way stop, and you drive 7 kilometers north. Let's draw a vector diagram and figure out our result. So, east. East is probably going to be best described as like north, south, east, west. So I'm going to draw a picture. Let's say we went this way. That's 10 kilometers east. A nice little arrow. You do your compass backwards?
No, it wasn't.
Oh, we lost.
North.
Lost it there.
Mike and Rod, please go to the cafeteria and see Mr. Yonke. Mike and Rod, please go see Mr. Yonke in the cafeteria.
All right, so there's your 10 kilometers east. For our next one, I kind of glossed over this a little bit here. The best method is to draw these things tip to tail. So here's the tip of my one vector. Starting here, I'm now going to draw another one going north. And I'm going to make sure that I don't draw it quite as long, right? Because this one's 10 kilometers, right? It means this one right here has got to be shorter for our 7 kilometers north. Where's our resultant? So the resultant would be like the from start to finish. So if I had to draw that, I think yeah, it's the hypotenuse essentially, right? Your resultant would be from where I started to where I finished. This is known as a resultant. So a resultant's going to need 2 things, right? It's going to need to know how far it is, but more than just how far it is, we're also going to need to know an angle. So why don't you guys give this a try for a second, because I think you have the skills to solve this, and I'm going to see if I can troubleshoot the computer here, because we lost them. There's one in the bin over there, I think. Is that one over there just like crapping out? That sucks. crest on the other end. They're like running blind. Absolutely, yeah. Right. So when you get your angle and your hypotenuse, make sure you actually round it accordingly. Well, you guys probably have some values here. If you do Pythagoras theorem, so 7 squared plus 10 squared. I need a square root. What did you guys get for the resultant as a magnitude? Exactly 12 or 12 point something? 12.2. So with only 2 sig digs, this would be 12 kilometers. Now you can do SOHCAHTOA, you can do any of those ones, but the advice I'd give is that 12 is really 12 point, and it's an irrational number, right? So I would recommend when you solve for the angle right here, I would do tan inverse of, oh, you're back. Nice. I would do the tan inverse of 7 over 10. Right. You could have tried the sine inverse of 7 over 12. You could have even done the cosine inverse of 10 over 12. But I wouldn't recommend those ones. You guys get what I'm saying there? Because you'd have to use the exact non-rounded value of that 12 value. So tan is almost always your best option. Hey, sorry that got lost. Hopefully you guys didn't fall too far behind. We're still doing that same example. What'd you guys get for an angle? You guys get that as well? What'd you get for the angle? 35, you're all on the same page? Okay, awesome. So let's talk about a few ways of writing this then. You could write it like this, 12 kilometers, and you could just say 35 degrees. The reason why that would be valid is that based on kind of this system right here, we always start with 0, 90, 180, 360. And so this right here being 35 degrees, that's an option. You could have written that. You also could have written 12 kilometers. You could have said you're going mostly east, and then you're going 35 degrees towards the north. That's another way that would be valid. Thanks. Third method would be saying 12 kilometers. Okay, thanks. G-strings? For me, G-string. Maybe I'll actually come over here. Anybody else follow that? Yeah? Walker?
Okay, bye.
Thanks. Okay, does that make sense to everybody? You good? Okay, let's fast forward a little bit here. I'm glad things are going well. Okay, what happens if I up the numbers here? So we're not just working with one number, we're working with 4 numbers. Can we still draw this? It's kind of going to look like a triangle at the end of the day, but it's going to look a little funnier first. First, we got to go 3.5 kilometers. So in a way, I've got to go up. I'll make north up, 3.5 kilometers. Then we go 4.2 kilometers east. Then we're going to go south by, again, make sure you're roughly to scale, 2.1 kilometers. And then we're going to go east some more by 1.1 kilometer. So now maybe it's a good time to talk about the whole tip-to-tail concept. See how every single one of those arrows, I've drawn an arrow, and then where the arrow part of my arrow is, that's where I started the next one. Does that make sense? That probably seems so intuitive, like so logical. That should be 2.1, by the way, 2.1. But some kids, for some reason, they do something like this. They would go up 3.5 kilometers, and then they'd like do this by 4.2 kilometers, and then they might go, like, you see how that's going to kind of cause some issues doing it like that? All right. So basically, you're just doing a continuation of where you start. Long story short, we don't really have a triangle in the same way here, do we? But we kind of do, though, if we're clever about it. So I'm going to use a new color here. I do need to go from start to finish still. So in purple, this is known as my resultant. And in a way, what I have to do is I have to make my own triangle. I have a triangle that looks something like this, maybe. So I can kind of draw my own triangle in there. And you're probably a little ahead of me on this. How far is it from here to here then?
5.2.
6.3?
It's 4.2.
4.2 and that's 2.1, right?
Oh, no,
Oh, I did it the wrong side. Sorry, my bad.
Guys.
No, you're right. You're right. I'm screwed up. I thought, yeah, 5.3. Sorry. You're right. I'm wrong. Okay, does that make sense to everybody except apparently me? So take your 3.5 and add your 1.1. Okay. And then for the other one, you're subtracting, right?
4.2.
Oh my goodness. Yes. Okay. 4.2 and 1.1 gets added for this one. We're cool? Okay. 3.5 subtracts 2.1 for 1.4. Do basic math in my head anymore? Alright. Everybody's okay with that? Honestly, it's really not that much more of a challenge unless you can't. Yeah, it happens. Alright, at this point here, it's Pythagoras' theorem again, right? So, 5.3 squared plus 1.4 squared, square root the whole shebang. That'll get you, I'll write it right here in a new color. That'll get us our resultant right there. 1.4 squared, 5.3 squared, square root. Shout it out when you have it. 5.5? Cool. Okay, so it looks like our magnitude is 5.5 kilometers. And then I would tan inverse the opposite over the adjacent for our angle. I mean, just based on rough visuals, I'm going to guess like 20 degrees, give or take. 15? Sounds about right. Everybody okay with 15 degrees? Okay, so a couple of ways of writing it. Again, we're kind of always going northeast right now. We'll change it up eventually, right? But you could have written it as you're going mostly east. You're going 15 degrees towards the north. That's an option. You could have written it as 15 degrees north of east. Because this is defined as 0, up is defined as 90, over this way is defined as 180. You could have even just said 15 degrees and just left it as that. So far, so good?
I think so.
Nice. Okay, do I have 2 examples left? One, I gotta do this one. This one here. Okay, no, we can finish this in the right amount of time. Okay, here's a new word I want you guys to know. Let's say I give you a vector coordinate. Could we find the components? By this I mean I'm going to give you the hypotenuse. Can we find the x and y values? So essentially, here's what I'm saying here. A plane is flying northwest. So drawing a little compass, north, south, east, west. We're finally going in another location, right? North 30 west means that it's going to look something like this. This is going to be mostly going north, but we're going 30 degrees towards the west. You guys see how that's working this time here? Go mostly north, shift off in the west direction by 30 degrees, and we're flying 34 kilometers. Now my question for you is, could you calculate an x and a y component? Could we go backwards? Can we use Pythagoras' theorem? We don't know, we need to know one of both sides, so that's not going to work. So this is where the rest of SOHCAHTOA would come in handy. So I'll just write it out again, SOHCAHTOA. Let's start with the sine one, because that actually worked out well. If this guy is our angle right here, down here is the 30 degrees. Who's the opposite? X, yeah. I'll just write it out here. You'd be the opposite. This long side right here is your hypotenuse. So by default, this is the adjacent. So I'm going to write out a statement here. Sine of an angle is supposed to be equal to an opposite over hypotenuse. Well, what values do I have? Well, I know the angle is 30, right? Do I know the opposite? Let's call it x. Do I know the hypotenuse, though? 34, right? Mathematically, how do you get x by itself, then? Yeah, just times with 34, right? So, word of advice here. Do not type this in your calculator. Do not type in sine of bracket 30 times 34. Your calculator believed that you wanted to take the angle and times it by 34, and so you're taking the sine of like an angle of like 1,000 degrees, whatever it happens to be. So don't do that. If you are going to times it up, I would say do one of two things. Either type in your calculator 34 sine 30, like I would type it in like that, but make sure that there's no chance of that 34, your calculator somehow interprets that it's going with the degree sign. Did you get a number? 17? Oh, so this is 17 kilometers. Can we throw a direction on that though? Which way is the 17 kilometers going? Yeah, west, right? Okay, for the other one here, let's write out the cosine. Cosine of an angle is equal to the adjacent over the hypotenuse. Again, I know much of this information. The angle is still 30 degrees. The adjacent is a y value, and the hypotenuse is still 34. So just times up the 34. What'd you get? Say that? 29? Okay. So that'd be 29 kilometers, and then this one, by virtue of it being going up, we would have to call it. Does that make sense? So if I ask you to find a resultant, it means find from start to finish, find the hypotenuse. If I give you a resultant, we could look for the x and y components of it. All of this really requires good trigonometry skills. Okay, I'm going to, this last one here is really the same as this last one here as well. They really involve one final scenario, which is known as the cosine law. I'm trying to think about the best way of showing this to students who have done it and haven't done this. You know what? Let's start with this example, the one that I've got next here, and yeah. Okay. Let's start drawing a diagram here. You're going to go 34 kilometers north, 30 west. So north, south, east, west. North 30 west would be in this quadrant here. So if I go 34 kilometers, sometimes what I like to do is I just draw in a little bit of a grid axis so that I have an idea of where things are at. And I know that this angle right here is 30 degrees. Can I see how I've done that here? This little axis I've drawn in dotted lines here, it's not actually a vector. I'm just doing it to try to get some perspective. Because what I'm going to do for the next one of these is as soon as I get here, I'm going to draw another little grid axis. Because now we have to go north, but 40 degrees east. Which means I need to go back this way. And my little angle would go right there. Is this nice and even and like north and stuff? Like, is it lined up perfectly like a nice right angle triangle? Unfortunately, it does not. But there is a way to solve it. It just helps if you've done grade 11 math all the way through. Sorry. Kind of stinks. Ultimately, our start is right here. Our finish is right here. Our resultant needs to look like this. Everybody kind of get the setup of how this works here? So, since we're not going directly north, or directly south, or directly east, or directly west, we have a huge problem. This triangle that I've drawn in here is not a right angle triangle. I don't think I can guarantee that. This angle right here, I don't know that it's 90 degrees. So there is a way of solving this. Again, we do this in grade 11 math. It's called the cosine law. So let me walk you through how a cosine law works. It's actually very straightforward. The cosine law looks like this. C squared equals a squared plus b squared minus 2ab cosine capital C. This is on your formula sheet? Okay. For those of you who've done this before, you'll recognize, even if you haven't done it before, you'll recognize I've shown you this. It looks very similar to Pythagoras' theorem. Very, very similar to Pythagoras' theorem. In fact, Pythagoras' theorem is actually the cosine law. We just have cheated. You guys in grade 11, grade 12, you guys remember why it's the same thing? You remember why Pythagoras' theorem, we don't bother counting this stuff here? What's cosine of C? If we have a right angle triangle, what's the angle in a right angle triangle? Yeah. If you try this in your calculator real quick, the cosine of 90 is 0. So what ends up happening is anytime you have a 90-degree triangle, you would always type in the cosine of 90. 90 is therefore 0, meaning that all of this stuff right here is never relevant. The truth is when we taught you guys how to do Pythagoras' theorem back in grade 8 or 9 or 10, we actually taught you how to do the cosine law. It's just with one requirement. We always gave you 90-degree angles, which meant that you didn't have to do the whole second half of the formula. Okay. The only twist now is that if the angle is not 90, whatever this angle right here is, that is known as angle C. That's all. That's the CliffsNotes version. So if the angle is 90, you can kind of skip this whole thing. If it's not, then we have to find that angle. In terms of how this works then, it does not matter what is leg A or leg B. So I'm just going to define this one as A, this one as B, and this one as C. And capital C, I should draw it a little bit different here. Capital C is always defined as being the one that's across. Capital C is always defined as the one being across from little c. So it's actually not that challenging. We don't know what C is, but I do know what A and B are. It's 34, and what's the other one? 58. Okay, we gotta pause for a second here though. We need to know what that angle happens to be right here. If it was 90, and it's a nice right angle triangle, we would never have embarked on this second half of the cosine law formula. It would not have been necessary. We call it Pythagoras' theorem. But we need to try to calculate that angle. So what I'd like to do here is I'd like to zoom in really closely on this section right here and see that we can try to calculate what that angle would be. So I'm going to redraw it. Over here to the side. You guys see how there was like a 40 degrees sitting right in that little section right there? Right in here, there's a little 40 degrees. That was part of a grid line. If this is 40 degrees right here, what would this angle right here have been? Yeah, 50, because it would add up to 90. Yeah. So what I could have said right here is that this is 50 degrees right there. I know it's kind of getting messy in there, but there'd be a little 50 degrees right in there. 50 degrees would be part of the angle I'm looking for. It's not exactly half of it, but it's one of the two parts of it, right? There's a 50 right here. I now need to kind of continue this grid right here. This would have been the line that exited, but there also was a line coming in like this. But I didn't actually have any of the angles involving there. What I do know is that way back here at the start over here, there was a 30 right here. You guys kind of see how I'm redrawing this again here, but a little bit nicer. There's a 30 degree sitting right here. Well, here's a nifty trick you can play here. That would kind of be 90 degrees here, right? Because this would have been north, and that would have been directly west. So if this is 30, and that's 90, we could actually figure out what this remaining angle is here. This triangle's out up to 180 degrees. What would this angle here be? Does that make sense to you guys? Okay, good. You're getting like an entire lesson crash course in 10 minutes. Long story short, we now know what this entire big angle would have been. The entire big angle here would be 110. This is really not that much harder than Pythagoras' theorem. It's just the actual full formula. So you'd type it in like this. 34 squared plus 58 squared minus 2 times 34 times 58 times the cosine of 110. Normally, this whole second half of it, we would have skipped because it would have been the cosine of 90, which is 0, which just wipes the whole thing out. Don't forget to square root, though. Just like with Pythagoras' theorem, you do have to square root. So hopefully you get 77 kilometers. That's how far from start to finish it would have been right here. That makes sense? I'm going to redraw this triangle one more time just to make sure that it's not so messy. Because after a while it does get a little bit filled up here. So essentially we had a triangle that looked something like this, it looked like. This side was 34. This side was 58. And this side now I've calculated is 77. So far so good. And one more thing I can plug in is that this angle right here we calculated was 110 degrees. But I'm not done though. That 77 kilometers needs to have a direction afterwards. Which means that I need to try to calculate this black line's direction. It's going north mostly, right? A little bit to the east. But the question is, how much to the east? You guys see how, like, right in here, this little sliver in black is going to be how slightly off to the east it happens to be? It's just slightly out. Right? I need to try to find a way to calculate that. To do this, we're going to use the other rule that eventually you'd learn. It's called the sine law, and that one's also on your formula sheet, right? The sine law on there? Sine A over A, B over B, C over C. Yeah. So, again, crash course, sorry. It's not ideal. So, what ends up happening here is there's another formula on your sheet that looks like this. Sine of, did they do it like this on your sheet? They flipped it? Okay. I'll do it the other way then. So this is known as the sine law. It's A over sine A equals B over sine B equals C over sine C. Since I'm already kind of going a little longer than I wanted, I won't give you the whole explanation about how it works, but we're going to talk, okay? I promise. I'm not going to leave you hanging on this. But essentially, this is actually where SOHCAHTOA came from. I actually had a proof for that I would have shown you, based on how 90 degrees is work. We defined this is A, and this is B, and this is C. This would mean then that this would be big angle C, because it's across from little c. this A right here makes this capital A way over here, because it's across from capital A. And this little b down here makes this one down here big B. The way the cosine law works then is you only ever need to have, like, you can either work with A and B, or you could work with A and C if you wanted to, or you could work with B and C if we wanted to. And in this particular setup here, I would like to work with, what did I do here? I want to work with B and C. I'm going to work with just this portion of the formula. So I'm going to write out here that little b over the sine of b is going to equal little c over the sine of c. This is known as the cosine law formula. Or sorry, this is known as the sine law formula. I know little b value right here, right? It's 58. Do I know angle B in the corner right here? Oh yeah. I'll come back to that. So I'll just leave it as sine of B for right now. Do I know little c value right here? I just found it actually. I wrote down 77, but I need to use the exact value. So someone help me out here. Can you search back in your calculator and find out exactly what it was? And obviously there's more after that still, but that's enough for now. And lastly, we need the sine of capital C, which is this big angle right here. That's 110. How do I get our one remaining variable by itself? How do I get B by itself mathematically? How do I get something off the bottom of a fraction? That would work. So times the sine B up to the top of the other side. So essentially now what you have is this guy's gone and sine of B is sitting up here. It's good, but I don't want the 76 and the sine 110. So they've also got to algebraically move. So the sine 110's got to come up top there, and the 76 has kind of got to come down to the bottom. Long story short, the 58 is going to have to times by the sine of 110. And it's going to have to divide by 76.6089. And that will get us the sine of B. Don't inverse sine it yet if you could. Just tell me what the value is going to be if you do 58 sine 110 divided by that value.
0.7110.
That'll do. Thanks, David. So hopefully you can get to this part here then, where we can find out what the sine of B is equal to. 0.7114. But I don't want, like, that cannot be the angle, right? This angle right here can't be 0.7 degrees, right? Mathematically, how do you get rid of this sine? You inverse sine both sides. So if you inverse sine this side and inverse sine this side, now we'll finally get what B is equal to. So I need to inverse sine that number. What'd you get?
45.
Perfect. Whew. Beast of a question. Okay, that's actually not the answer. I gotta go back up to the original diagram here and show you something. A little while ago here, I drew a little sliver right here. This thing is going to be going mostly north and a certain direction towards the east, but it's not going 45 degrees towards the east. Because what we calculated is that this whole angle all the way around here was 45 degrees. The whole angle was 45 degrees. 30 degrees of it is actually over here in a section we don't care about. So the little black sliver, the sliver that actually goes off on the side of east there, would be 15 degrees. Does that make sense? Because the whole angle down here is 45. cut out the sliver of the 30, and there's our answer. All of that work to tell us that it's 77 kilometers going north 15 degrees east. Okay, you guys have done this before, right? Does that kind of jog your memory? It's like we spent a whole unit on this last year. You can kind of see where it kind of comes in here. I'm so sorry, guys. I had to choose between the algebra unit and the trig unit first. I think we need to do a tutorial on this. I can help get you up to speed on this. It's not the hardest thing we did last year, is it? Okay. It's just, it would really help if we'd done it beforehand. So we will. There is another way of solving this where you don't have to use these new rules, but I think it's actually way more work. As believe it or not, as much work as that was, this would be more work. What you could do is you could make a triangle right here, a large triangle right here. You could make another large triangle right here, and another large triangle right here. And you could work with like a triangle, another triangle, and a third triangle. But you can imagine that the number of calculations you do using 3 different triangles would be like impossible. So essentially what you would do is you would find out this y distance, and add them together over here to get this side right here. You'd find this x distance, and subtract them to get this little bit right here. And then you'd re-hypotenuse them to get that side right there. But it's, if you can learn sine and cosine a lot, it's way more efficient. So, okay, I'm going to stop there. This took me a little bit longer than I had hoped. Cliff Notes versions of what we talked about today. I need you guys to be able to do some trig. I need you to know how to do SOHCAHTOA trig. I need you to know how to do Pythagoras' theorem trig. And if it can jog your memory, it really helps if you know how to do the cosine and sine law if you've learned that at some point in your life. If you haven't, let's do a tutorial on that. So, actually, you guys want to do that during focus time today? Or do you want to do that tomorrow? Like, when would be a good time to kind of do a little bit more work on the trig stuff? Okay. Let's do it tomorrow during focus time then? I'll try to help out a bit more with this formulas. Okay. Okay, I know I have another example here, but honestly it's the exact same thing. It's showing you how to deal with something where the angle right here is not 90 degrees. So essentially once you figure out how to solve that problem, this is C and little c, A and little a, B and little b. Okay. Yeah, for sure. Okay, why don't I pause the lesson here and we'll leave it there. If you want to, try the last example when you get a chance. See whether you can try to figure that one out.